Let's now look at a more optimized algorithm, the compactable algorithm. So, compactable was initiated in 2016, and it's quite similar to str2. The IDs are quite similar, but instead we are going to use a stateful sparse bit set to store the table and to have some pre-computed data structures. So we have still the table, we have still the main, we have still valid tuples, we have still unvalid tuples. That's still the same. But we are going to have pre-computed structures. And these pre-computed structures, they are called the supports. And they will gather in advance the tuples that are linked to a given value. So, as we are speaking about bit sets, they are a collection of bits, and bits can take two values, 0 or 1. In general, in our case, 0 means no, and 1 means yes. So, we will have what? We will have one bit in each of the bit sets, which will be for each of the tuples. So here, we have one bit, the first bit of the bit set, which correspond to the first tuple. These bits correspond to this tuple in each of the bit sets that we have. And our bit set support, here, they are all associated to one value, one literal that we seek to support. So in this case, x equal to 1, in fact, we are going to gather all the tuples that have x equal to 1. So here, we have 1, because 1 is the value here for x in this tuple. And the next tuple is this one. So we have a 1 in the bit set. And these are the only tuples with 1 for the x. So these are the two ones here. Then we have x equal to 2. We have 1 here and 1 here. Also here and 1 here. We have 4 of them. So we have the 4 bits set to 1. And so on for each of the values assigned to variables. Okay. Now, how can we compute the valid tuples? Well, valid tuples, they are also a bit set that will gather which tuples are valid. So again, 1 means yes, the tuple is valid. 0 means no, the tuple is not valid. So we want this result, which is the tuples that have values in the domain. So the domain were 1 through 5 for each of the variables. So the valid tuples are the green one. We want 1 there and 0 in front of the other. Well, to see if one of the tuple is supported, we can do bitwise operation between the supports. And in fact, it's easy. We will just do a bitwise OR. So the bitwise OR is if one of the two is 1, then it's 1. And we will do this bitwise OR between all the support for a given variable, so here x, with all the value that we still have in the domain. So 1, 2, 3, 4, 5. So these are these OR between all these supports gather in fact all the tuples from the table that have one of these value. And we will do that for y and for z. So we have the first operation here leads to a bit set with all the tuples with the given value for x. The second one, all the tuples for the given value of y. And the last one, all the tuples for the given value of z. But the thing is, we want all the tuples that have the right value for all of them at the same time. So that's why we are going to use the logical AND. Logical AND, it's if you have both of them, so if both bits are put to 1, you still have the bits as a result. But if at least 1 is put to 0, well, it's not there. Because here you want all the tuples, or all the tuples to be in all of these 3 sets. We'll need the logical AND. So, if a tuple is in the set which is valid for x, in the set for the tuples valid for y, and the set for the tuples valid for z, then it's a valid tuple, because every value is valid in it. And so this is how we compute the valid tuples. So, now that we have updated our table, we can filter it. And to filter it, we need the values that are not supported anymore. So the one where there is no valid tuples for this given value. And we are going to use again our logical AND here. So again, as in s02, we are going to try for all the variable, all the value, and we are going to do a test, which is the intersection between the valid tuples and the support for x, for the given value. So we are going to do the intersection between all the valid tuples and the supporting tuples for the value that we want to test. And if the intersection is empty, that means that there is no valid tuples for this support. And if there is none, the value is not possible, so we remove it. And this is why it is done with bitset. So we look here, we have the valid tuples. We intersect with the support for a given value, x equals 5. We see that there is only 1 bit here, and the logical AND between the two is 0. So, and the logical AND with all the empty there, it's also 0. So we don't have any intersection between valid tuples and the support for x equal to 5. So we can remove it from the table. Okay, now we have seen the how to have the valid tuples and how to filter. But to get the valid tuples, we have in fact 2 possible strategies. So the first one that was already presented is the method from scratch. So what is done is that we compute the logical OR between the remaining value for each of the variable, and we do the logical AND in between. And here it's from scratch because at each time we are going to recompute completely the valid tuples. Okay? And the second one, well, imagine you don't modify all the domain. If you don't modify the domain, well, there are parts here. If you modify only x, for example, well, the valid tuples from y and from z, they are the same. So what we can do is take the previous value of valid tuple and only do the logical AND with the new logical OR between the new value in the domain. So by doing that, we avoid doing all this logical OR and here too. And this is called incremental update because we are only doing the update by what has been modified. So in this case, the domain of x.